Hi, this is Steve, V6WZ. I'd like to show the design and construction of my 9-circle receive array combiner board. This is really nothing more than a duplicate of the 9-circle array designed by John W1FV together with the YCCC contest club there, and they put together a kit which is marketed by DX Engineering. They're no longer sold by them. And I have one, and it's been a great array and performed very well. But I just like building things and decided to design my own combiner box. By the way, I've also designed and made available online by way of a video and provided the PC boards for the preamps, for the small vertical elements as well. This design, the board, the one thing I did do, really nothing's changed from the design by John, other than in the bottom corner here you can see I've added integrated on the board a 2N, a 5109 preamplifier. These arrays all require amplification, as far as I'm concerned, and so I thought, why not? Since I found I could fit it on one board, I integrated it on here. So the board. What I'll do is provide a link, like I've done before, of the PCB design, which I made in KiCad, and you can download that and use your preferred vendor to have it made up for you if you'd like. Having said that, my intention with this video is not to provide a step-by-step instructional video on how to build this. Really, all I want to do is provide you with the board, and it would be incumbent upon any builder to read the documentation, which is available online, and I'll include that link as well. DX Engineering provided the detailed assembly information, and substantially it hasn't changed with my design, in terms of winding the transformers and whatnot. But it's incumbent upon anyone that wants to build this to be able to understand yourself how to essentially assemble this. All I can do is provide the circuit board. Just give a quick explanation as to how the 9-circle receive array works. There are 8 verticals surrounding one central vertical. All these elements are identical. They're usually 20 to 25 feet high, and they're fed with high impedance amplifiers. At any one time, there are only 3 elements active. And through the antenna modeling, which John W1FV did, he derived the optimal phasing, relative phasing of these 3 elements to provide a enhanced or optimal RDF, receive directivity factor, in one direction. And then using a relay matrix, these 3 elements can be interchanged to, for example, reverse the direction, so that these 3 elements can provide 2 directions. And then that same relay matrix then can select another 3 elements to achieve the same 2 directions, and so on and so forth, to provide 8 full azimuth directions. So therefore, at any one time, we only really need to worry about how to combine 3 elements at any one time. This, in fact, is the schematic of the combiner circuitry. And you'll notice in this case, antenna 2 is representing the central element, whereas antenna 1 and antenna 3, shown here, will be going to the switching matrix, the relay matrix, in order to change direction and azimuth. The phasing is achieved using delay lines, a delay line 1 and a delay line 2. For example, delay line 2 on the central element is minus 200 degrees, minus 40 degrees with antenna 3 relative to 0 degrees on antenna 1. John's also included a T attenuator to account for the losses in delay line 1. And these 2 antennas 1 and antenna 3 are then combined with a magic T, or a 0-degree hybrid combiner, T3. 275 ohm antennas combined will have an output of 37 ohms. And the antenna 1 through its delay line is stepped down in impedance from 75 ohms to 37 ohms to match those other 2 combined antennas. T4 is a phase reversal transformer, 180-degree phase shift in T4. There's also another attenuator here made up of R2, 4, and 3 to account for the to match the gain of the antenna 2, because you've just combined 2 antennas, so this needs to be stepped down so that the amplitudes are the same. These 2 37 ohm outputs are combined in another magic T combiner, T4, transformer T2 rather, and of course 2 37s have an output of 18.5 ohms. And of course, that needs then to be stepped up to 75 ohms, and that's what T1 does. This is one thing that has changed in my design because I've integrated on the same board that preamplifier. It's a 2N5109 amplifier, and it has an input impedance of 50 ohms. So I've made one modification here to this transformer. Okay, I realized, of course, in the last segment there, I had rounded this off. Of course, 275 ohm antennas combined is 37.5 ohms, and of course, 237.5 is 18 3/4 for accuracy there. This is a schematic of the relay matrix, which either switches direction of the three elements or will select any of the other combination of elements. And so basically, I worked with KiCad and essentially followed John's schematic exactly. Kind of in this section, you can see this is the relay switching matrix, and then to the left here, this is the combiner circuitry. And this is the output transformer, which, as I just mentioned, could either be configured to match the 50 ohm input of the 2N5109 amplifier shown here, or I've even put on the silk screen, you'll see some notes where you could do the 10 to the 10 turn center tap transformer, and then include a jumper to if you wanted to eliminate the preamplifier. I don't plan to talk in a lot of detail about the 2N5109 amplifier circuit because I do have another video, which I'll include the link to at the bottom of this video. And what I do is describe the prototype that I built. In fact, another PC board layout for this amplifier standalone. And in fact, I'm currently using it. This is the classic design by Larry, W7IUV. And I talk in that video about how he's optimized the component values for IMD and whatnot. I also, using my VNA, show how I characterize the input impedance of this amplifier because it's vital that the output from the 9-circle receiver array sees its characteristic impedance, either 75 ohms or 50 ohms. In my case, with the amplifier, I've got that amplifier so that it'll see 50 ohms. And the testing I did does show that this amplifier is very accurately matching a 50 ohm input impedance. I've also included a T attenuator on the output, and I show how that really helps to buffer any kind of variation in the output impedance, any kind of mismatch with your coax line going to the shack. I encourage you to look at that video so you can understand the specifics of the amplifier here. Here's the KiCad PCB layout design that I've done for the board. I must confess right away that I greatly relied on John W1FV's good work in terms of laying out the relays. In other words, the relative position of these relays to optimize the geometry and most importantly minimize trace conflicts. It's a bit of a Rubik's Cube to try and get these relays in a position where you're not having to jump too many traces. So that was a great help to get the relay portion of the board laid out, which is shown here. The other thing you'll notice is some of the trace widths are different. I was able to rely on some of the great calculators online where I can input the board thickness and the dielectric characteristic of the board together with the trace thickness and derive a trace width to achieve a characteristic impedance, so that, for example, the 75 ohm lines are kind of this thickness, and as we step down and split and combine the various antennas and impedances, I've changed the trace width to at least try and get close to the characteristic impedance. Truthfully, I'm not so sure it's super critical, but just try and minimize any kind of impedance bumps. One other thing on the silk screen I've done is I've endeavored to annotate as much as I could. Let's go to the 3D view here. First of all, one thing, the actual values like R12 and R10, those are not the same numbers. I forewarn you that is shown in John's schematic. Those are specific to my KiCad schematic, but all of the component values are properly and accurately shown on the silk screen. I did, though, make sure that the transformers are properly labeled. T1 is T1 and T2, T4, and so on and so forth. Those transformers do match those described in the literature, in John's documentation. I've also annotated those transformers which are tapped. I've tried to give some information, 7 turns tapped, 5 turns from ground, and I've tried to note it on the silk screen as to which tap is where. This particular transformer shown here, this is that output transformer I was referring to, and in this case, I've kind of made a note. In other words, if you go 10 turn center tapped, that would be for the 75 ohm type of situation where you choose maybe not to use the amplifier, whereas 8 turns with tap 5 turns from ground, that's your 50 ohm situation where you are going to use the amp, and I've kind of noted those on the pinout. And regarding the amplifier, you'll notice here I've also made a point here where you could jump if there's no amp. There's a jumper noted J1. So if I zoom out, if you don't want the amplifier, you'll put a jumper from J1 to J1, which basically just goes right out of this transformer to the output RF connector. You can see my attenuator here in the 2N5109 amp, and so yeah, that's the look of the board. All right, proceed along and populate the board with all of the components. As I had already mentioned, do not follow the component names. Follow the component values. The component values are carefully shown on the board, and those do accurately reflect the schematic. The transformers, there's some great documentation and really concise detail in the YCCC documentation that's provided at the end of the video. Shows you how to wind these. And it's very well described. On the silk screen, I also indicate, fairly carefully where the taps are and which tap goes where. And so hopefully you can follow that along and have no trouble with the transformers. I'll tell you right now, that's probably the biggest place where an error can occur, is getting those transformers wrong. I'll give you a brief description on how you can test the board at the end and identify those problems. I put a little bit of double-sided tape under each transformer just to sort of secure them to the board, just to prevent any perhaps vibration causing the wires to break off or come loose from the board. I think that's a good preventative measure. Make sure you put the connectors on the back side, right? Because, of course, when you mount this thing on the lid of whatever box you want to use, I'm going to use a metal box. I think that's going to be kind of cool. Maybe minimize any common mode noise. You want the components to be, on the outside, right? If you're following me, and so make sure you got the connectors on the right side. The other thing to drill out the board, it's really easy. So on the lid of whatever box you select, just take the board, and again, you make sure that you've got it the right side up. In other words, the component side up. Center it on your board. Pretty easy to do, and then just take a marker and just mark the center pin of each one of the F connectors. And heck, I've got a drill press, but I'm sure you could drill it out with a hand drill, as long as you're fairly careful so that they line up. And I've included a barrier strip, terminal strip, which has screws on it. That's in the BOM that I provide, and that'll be the connection for the 12 volts as well as the grounding control lines for the various relays. As I say, I do provide a BOM, bill of materials. I think it's pretty accurate. Hopefully it's accurate. Let me know if you see something missing. But hey, listen, that leads right into one last comment here. It's probably the second time I've said it. I might say it again, maybe at the end of the video, but do not even attempt to build this thing unless you've fully read and fully understand the YCCC manual, which I provide the link to. Look, this is in no way meant to be a step-by-step instruction. I have no interest in doing that. All I'm providing is a file for you to download and maybe get your own circuit board made. I'm not selling anything here, and I really don't have the interest in providing a step-by-step manual on how to wire this up. One thing I did forget to mention was the 2N5109 amplifier circuit. That's, of course, not described in any of the documentation that John has, but I did mention earlier, and I encourage you to watch that video that I include. I have the link at the end of this video, and it describes all of the details in terms of the documentation for winding that transformer and setting the bias resistor for the correct current and things such as that, and the need for the heat sink. So have a look at that video too to guide you through any questions you might have on the amplifier portion of the circuit. Okay, here's my final board install on the lid of the aluminum box. The pinout for, one thing I didn't mention, the pinout here for the relay control lines, which are taken to ground to activate each direction selected relay, is well described in the documentation. both the relay logic as well as there's even a controller board described where you could use a rotary switch to control the direction. I'm not going to talk about that. You can use your own system. For myself, since my station is remote, I have built a PC controllable rotator using the program called PST Rotator, which drives a USB relay board, which in turn drives these relays. And I actually have another video on that if you're interested. Gosh, I think it's pretty handy to have the controller available on the PC. Hey, one other thing, I kind of goofed up here or made a bit of a layout error in hindsight, right? That happens sometimes. I ended up, for some reason, deciding to put the terminal strip here for the pinout on the relay controls, but it kind of is crowding this 1F connector. I mean, it'll still work. I can still get in there, but there's no need to have done that. I kind of should have put that down here. So heads up there, just keep an eye on that. These things happen. Anyway, ready to go in the field. Put her on the aluminum box, and we'll do some tests next. So here's the field installation. I've used a plastic box, a big storage bin that I got from a home building supply store. I had to fashion a wooden or a plywood cover for it because literally a moose ate the cover. He completely cracked and consumed most of the cover, so I had to build this wooden one. Anyway, there's the box. It's installed inside this container to just to keep things dry. The delay lines and the extension for the center element is held on a bracket. The chokes on all of the feed lines going to the individual verticals are these large type 31 clamp-ons. This is different than what was described in the YCCC manual. The purpose for these chokes is not common mode. It's not to prevent common mode noise. It's designed to prevent the feed lines from upsetting the pattern, because they all come together here, and if they're all tied together and therefore grounded, you kind of end up with a ground screen which upsets the pattern. The truth is, I'm unsure if this is ample isolation. I'm also have heard that it's best to not have these close together and separate them. The fact is, this array is performing extremely well. I've had no trouble with it. So at this point, I'm going to leave it as is. I may eventually, just to try, and I'm always trying to improve the station, maybe endeavor to even increase this isolation more. But as I say, at this point, it's working just great. I decided I'll make a separate video for the testing of the box. This video is already getting a bit too long, and it would only interest those that decide to build this. The reason for the video, though, is there are some differences between the testing description that John provides in the manual compared to mine, simply because I have that amplifier integrated onto the board. But the testing I did do showed the box to be to test exactly the same as the marketed one by DX Engineering, and the performance so far has been excellent. One thing I will mention, if I'm going to post all of the links at the bottom of my video, and as you probably know, though, when you go to my video at the bottom here, there's the dialogue right under the video, and you need to click Show More, and it's there where all the links will be. In those links, I'll, of course, as I said, include the manual, the YCCC manual, so you can reference that. The PCB KiCad file will be there, as well as the BOM, the bill of materials. Hopefully that's correct, but look, I suggest you use it as a guide. I mean, select your own components. I mean, perhaps you can economize on some of the components I've selected, or maybe you want to amp up the capacitors values or the capacitor types if you're so interested. I'll include the link to the 2N5109 amplifier video. Important to look at that, I think, because I explain testing, or not so much testing, but adjusting the bias resistor for getting the amplifier properly adjusted based on the device you're using. And also, I'm going to also include a link to these guys, the PI4CC Contest Club. These guys market boards, and this might be a better solution for you if you want. These guys actually sell these boards both for the individual high impedance amplifiers. I've designed my own, which I prefer actually than this particular mechanical layout, but this follows the YCC design. But they also sell both the relay switching board and combiner board. They've kind of broken the board up into two rather than integrating it together like I have. But of course, the other difference with mine, I've included the integrated the amplifier on the same board. But you know, this is a good option too for those that might be interested. Anyway, that's it. Hopefully, this has helped you guys. And if you're interested, good luck building. These 9-circle arrays are great. I've been really happy with the performance of this receive array. 73, Steve, V6WZ.